All right, hey everyone, Rob Case here. This is the Dropping In Surf Show. Thank you to the 5 of you that listen to this on a consistent basis for your patience. It's been a while since I've recorded. I have a whole bunch of ideas and shows coming up that I'm excited about. Had to take a little bit of a hiatus to get some things done, but I'm back and I appreciate your patience. For those of you that don't know me, I am a paddling technique coach located in Northern California. And this show is about science and math in the world of surfing and how we might gain some sort of improvement or knowledge or information to help us improve and have more fun out in the water when we're surfing. So today I'm extremely excited to cover 2 different studies that were released this year from one was in the Coastal Engineering Journal, which you see here on the screen. If you are listening to this in your car, I apologize ahead of time. This is going to be pretty visual, and I will do my best to try to describe what I'm showing on the screen, but I definitely think that you should come to the YouTube and to the show page to see the video to further illustrate this. But essentially, these are 2 different studies that happened in this past year at the Kelly Slater Surf Ranch by Scripps Institute of Oceanography. And you've probably already seen some of the results from it. You've probably seen some of the videos or some of the headlines because many of the surf major media publications have reported on these studies. And if you want kind of the Cliff's Notes version of that, those are great. But I wanted to know what wasn't said in the summary. I wanted to see, was there anything else in these reports as byproducts that we can maybe take and use to help us in any of the different facets of what we do when we go out in the water? And I found some good ones. So I'm going to share some of them with you. Almost all of these that I'm showing and I'm going to talk about today have to do with my level 2 course. Level 2 is all about wave catching, getting out, popping up, and ocean knowledge in general. That being said, an experienced surfer will find some of these results and be like, oh, okay, that makes sense. I've experienced that for 20, 30 years. I know what that feels like. For those of you that are more kind of on the beginner intermediate level, this might help explain what you've experienced a little bit more. It's a part of what I teach in level 2 that is one of the harder things to explain, especially around the duck dive or turtle roll and how long you need to stay under for. And so there's finally some scientific evidence, some data. It's very little, and so we're not going to hang our hat. We're not going to put all of our weight into this one basket and say, this is for every situation. This is one specific situation, one specific scenario, for example, with a type of wave. But it's the first time I've seen some scientific evidence and information behind the things that we've talked about. So with that, let's get going. So the first one is by the Coastal Engineering Journal. It was published by them, but it was conducted by the Scripps Institute of Oceanography. This was done in July of 2023. It's called The Wave Drifter, a low-cost IMU-based Lagrangian drifter to observe steepening and overturning of surface gravity waves and the transition to turbulence. So you may have seen some video. There's a great video on YouTube of this device working. An IMU is an inertial measurement unit, and it's basically like a gyroscope, and it measures the X, Y, Z axes. If you were to use Earth coordinates to describe it. The main kind of purpose of this that they outline in the introduction is really about how when a wave breaks, it transports sediment and it suspends sediment. And they wanted to kind of understand what happens after it breaks and how that flow might happen, how a water particle might move after it's broken, and in the process of breaking. And there are some limitations because this is at the Kelly Slater Surf Ranch, which is a different type of wave than that we see in the ocean. It's called a soliton wave versus what I guess you would call like a progressive wave in the ocean. But that being said, there's some really cool results that follow. So the IMU that they used was this like tiny little ball, and they did a few of these, and it looked kind of like this. It had the IM unit inside it, and on the outside it basically floated. And they had several of these in the pool at a specific point in the pool where they let it go and they let it get sucked up by the wave, got thrown over, landed in the impact zone, went through the whitewater, and it recorded information. And they did it many, many times. And these are the results. Now, they were able to, one, validate that this methodology of using this type of IMU, a wave drifter, was sufficient information to come back and help them determine things like the sediment spread and understanding waves more. But what we're going to really take a look at is what happens after the wave breaks, where, what direction is that IMU going, and can we maybe translate that into something that helps us with, say, our duck dive, or helps us possibly with our turtle roll, or the timing of things, or reading a wave better so that we have a better getting out strategy. So these are things, again, in the getting out portion of level 2, we talk about strategy and we talk about technique, and there are many techniques and there's a couple different strategies. This is one very specific type of wave. This is a plunging wave. It goes from top to bottom. It has the barrel, and it breaks a specific way. It also breaks a little bit different than, like I said, an ocean wave. In the beginning of it, and some of the water molecules and the way they move up the face of the wave, slightly different than the ocean. But for what we can get out of this, some of the results, it's very exciting. So let me explain a few of the kind of parameters. Okay, so the components. The wave drifter analyzed acceleration in Earth coordinates with components AX, AY, AZ, where AZ is the vertical acceleration with gravity removed. So just think, if X and Y were fixed, all AZ is how high it goes or how low it goes. And we're going to be looking at acceleration specifically on this study. So if it is a positive acceleration, it's going up. If it's negative acceleration, it's going down. Okay. So that's going to help us with direction. But it's the amount, it's the magnitude that's actually really interesting for us. And I'll get to that in a second. The horizontal acceleration component will be the Y. So when I think of kind of horizontal, I think of further back in the pocket to out onto the shoulder. That's the Y coordinate that they're describing. And they say it here somewhere. I'm trying to figure out where in the specific study that they do outline these 3 coordinate systems. Doesn't really matter. I'll just explain it. You can look this up and find it. But the Y coordinate, if I go to, I'm going to scroll down just to kind of the picture of a wave. Okay, so the Y coordinate, if we're looking at it, we're looking from above, from like a drone view, and we're looking at the wave cresting at the bottom of the viewfinder, and the shoulders at the top of the viewfinder. And so the Z is going to be like at the camera or away from the camera. The Y is going to be to the bottom of the screen, to the top of the screen, so out to the shoulder or further into the pocket. And the X coordinate, AX, is the acceleration in the same direction of the propagation of the wave, which basically means what direction is the wave going? It's going from right of the screen to the left of the screen. So in this picture from the top down, we're looking at a right wave, a right breaking wave. It's the right at the surf ranch. And so it's going from the right part of the screen to the left because we're looking down on it. Okay. So X is the direction the wave is going. Y is out to the shoulder or further into the pocket. And Z is going to be height. Okay. That's the simplest kind of description of it. Okay. So there's, they're going to use terms like overturning. That's a barreling wave. So this is a photo of an overturning wave at the surf ranch. A wave drifter is visible in the face of the wave, highlighted by the yellow dashed circle. So I'm showing now a straight on view of the wave of the right. And you can see like a little tiny device in the middle of the face, and you see a bunch of the scientists kind of duck diving under the wave. You get a few scientists taking video. So this IMU, this wave drifter, is coming up the wave face, and it's about to kind of get overturned, and then they're going to, and there's a few other ones. So the thing with these IMUs, they took a few different ones. So now I'm looking at the top down view, and you can see several of those IMUs kind of floating. And so they were able to get the IMUs at different points of time to report back information. So before we kind of look at the results of some of the movement, I want you to think about how a overturning wave breaks. So if we're thinking of a right, meaning, it's breaking from, if we're looking straight on, it's breaking from the right side to the left side. We're looking at a right. How might a water particle move? It kind of feels like it kind of goes backwards first. So it goes like negative in the X and then positive in the Y, and then it pushes forward, so it goes positive in the X, and then it hits, and then once it hits in this lip line, it's like, I don't know, man, it's anybody's game where this thing's gonna go, right? Because we've all felt that point of impact. And on a barreling wave like this, you can see here how high the whitewater goes. It's like, does this IMU shoot up and forward? Does it shoot left, right? Does it drive down to the bottom of the basin? Does it go through a bunch of different cycles? We've felt this. And so what we have tried to do in the past is anecdotally say, oh yeah, well, it rolls you a few times, but there's so much chaos in this whitewater. We haven't had any kind of strong scientific evidence of what is actually going on in here, and now we do. So I'm going to show you something. Now you kind of identify what these things are and what they're doing in terms of going up and over, and then they're detonating basically in the impact zone. I'm going to go ahead and show you some of the results. Here's just a few more pictures. Now it's a GoPro footage of being out on the shoulder, kind of out in front of the wave. And they're just highlighting kind of a movement of a singular wave drifter IMU. It starts about mid-face at time negative 0.6 seconds before impact. And then at negative 0.4 seconds, it's like hung up in the lip. Well, it's hung up in the top of the wave. The lip is already ahead of it. So this IMU is kind of like second or third in line. There's already one in front of it somewhere in this lip line. In the third shot, that same highlighted one is at negative 0.2 seconds from impact. So it's 0.2 seconds from impact. And it's now in the lip and it's heading down. And then in the last shot, it's right before impact. It's at negative 0.033 seconds. So we can kind of see that progression. And we'll refer back to this figure 6 when we're describing some of this. this is the illustration that I want us to kind of study a bit. So what we see on the screen is we see a line chart with several points. The x-axis of the line chart is the time from the drifter impact in seconds. So there is a -1, there's a 0, there's a 1, there's a 2, a 3, and a 4. And then on the y-axis of this line graph, we have Earth acceleration in g units. So no units, it's g. You know, it's gravity's been removed. So it goes from 0. It goes from -15 to -10 to -5 to 0 to 5. So just think of this as this is the acceleration of the IMU. It's not the speed, it's the acceleration. So it's the derivative of speed. Now, there are 3 different lines on here. There's an inset, and I'll get to the inset in a second. But there are 3 different lines here. They're different colors. AX, meaning the direction of the wave propagation. So think of it as far away from the beach or closer to the beach. That's X. Now, that's different. If you've taken my level 2 course, I call that axis y-axis, or timing. Okay, in this study they're calling it the x-axis. It's in the direction of the wave propagation. So I'm just making that distinction for any of you guys that have taken level 2. It's a little bit different. It's just so that we understand that this ax is the acceleration of that vector moving towards the beach or further out to sea. Okay, so think of that in your head. AY, in this case, is now closer to the shoulder or further back in the pocket or into the whitewater. So it's kind of like what I teach in level 2 is the x-axis. They're saying it's the y-axis. And then AZ is the vertical axis. It's the acceleration of the IMU vertically. Okay, so the blue is the x, the red is the y, and the yellow is the Z. And we'll start with the yellow. Okay, so the yellow is the verticals. Now you have to think, okay, acceleration, not speed, but acceleration of these IMUs. So as we get into that kind of -1 second before impact, you can see the acceleration go up. And then I'd say about half, at about -0.5, maybe a little bit before then, it drops dramatically down to about -3. So basically it kind of goes up slightly and then it goes down, right? So the acceleration goes down, then it comes back up, but it's still negative. So it slows down. So it's still going down, but it starts to slow a bit. Okay, in its acceleration. And then all of a sudden, at time 0, at impact, it shoots up almost to 5 G's for the units. So think of it as the -1 is that it starts to get sucked up to the top, and then you got to think it's not going to go up any higher. So the acceleration stops. And then all of a sudden the acceleration goes really fast in the downward direction, right? Because it's plummeting down to the lip. Now there's a point here right before impact where the acceleration starts to slow down a little bit. And then when it hits, all of a sudden the acceleration shoots up. So this thing pops up. Right? And I'm following the yellow line here. So at just after impact, like shortly thereafter impact, it shoots up. And then the acceleration starts to drop back down and goes negative at about a half second. And then it goes back positive at about a second. Now, not as high. It goes up, maybe it goes up to about maybe 2.5 units. And then it goes back down again at about a second and a half. And then it starts to come back up at about 2 seconds it has that, it goes up again up to about almost 2 now. So not all the way up to 2.5, but about 2. And then it goes down and then up again, and then drops down significantly when we're almost at 3 seconds. And then once again, it goes up again and then down again, and then it flatlines. At about, after 3 seconds, it flatlines. So think about this. And we're just talking about the vertical axis. So at impact, so it goes up, it goes into the lip, it comes down, it hits impact, and guess what? It bounces back up. All right? It goes up very fast in terms of acceleration. Then it goes down, pretty significantly down, at about negative 2.5. So it was up at 5, then it drops all the way back down to negative 2.5, and then it goes back up at about 1 second. It's at about 2.5, positive 2.5. And then it goes back down to negative 2. And then it goes back up to positive 2 at about 2 seconds. And then it goes back down to about negative 2.5 roughly. It almost gets stronger in the negative on the second kind of roll or the second cycle through it. And then it pops up to about positive 2, and then it goes to like negative 1, and then it kind of like flattens out. So there's a couple things we can take from this, just from the verticality of how the water particles are moving, is that I kind of alluded to it. There's almost like a cycle to this. It goes up, it goes down, it goes up, it goes down, it goes up, it goes down, it goes up, and then it goes down, and then it kind of flatlines. So within 3 seconds, it goes up and down 1, 2, 3, 4 times. Almost 5 times within 3 seconds. So that's that cycling motion that we may feel or experience where it feels like the wave is pile driving us down into the reef or the sand, and sometimes it feels like it's pulling us up when we're duck diving, specifically as I'm talking about when we're duck diving, right? So thinking about this, and I'm not there yet in terms of what the conclusion of how we interpret this is, but for a plunging wave like this, it is very clear it has these moments where it's pulling up and then it goes back down. So if I'm duck diving and I want to save energy, right? Because my whole thing is to catch the most waves with the least amount of effort, right? And that has to do with your strategy getting out, but also the technique that you use. So in terms of technique here, if we can identify this is a plunging wave, it's an overturning wave, it's top to bottom, it's barreling, where do I need to be in terms of the time after impact so that I can minimize the amount of energy that I'm using just from the verticality? How can I use this to my advantage? Now, John has mentioned this, I think, in a stab tutorial, and he got it from Mike Stewart, who's a professional bodyboarder legend, about this idea of this kind of bouncing cushion after impact, specifically for top to bottom waves. How you don't need to duck dive very shallow in order to kind of have this, all this water kind of bounce over you. And it's almost like they call it like a bubble. Now, they described it quite well. This gives specific evidence of that bounce. That's what excites me. It's incredible. This little inset in the there's a little inset in the graph, and it just shows kind of a zoomed in portion of the point of impact to just 0.4 seconds after. So very quickly, 0.4 seconds after, it's just this little bit, and it kind of gives some more detail so you can see the magnitude of the movement just in that very, very short half a second period. But it's very clear that there's the impact, there's the first bounce or bubble that happens, and it is about a half second in duration before it comes back down. So before it comes back down and then bounces back up again. So you have about a half second window to find that little first bounce. Now, if you don't get the first bounce, there's a second bounce. It's not as big. That second bounce lasts once again. It comes down, so it bounces up and over, right? So it bounces up and over and then comes back down. That's another about second or so, right? And then it bounces up again, comes down again. So there's another second, and then there's one final bounce at the end. So there's about 4 bounces just on this one wave. Now, each of those bounces gets smaller and smaller and smaller. Surprisingly, the last bounce before it flatlines basically and all the energy kind of dissipates it kind of gets like a second wind. So there's a big bounce at first. Then there's like a moderate bounce, and the third bounce is probably the least. And then there's a bigger bounce for the fourth one before it dissipates. So a couple things. One, we've got 4 bounces in 3 seconds. We've got flatlining afterwards. So thinking about strategy, if you're paddling out, and we're not talking about Surf Ranch anymore. We're paddling out. We see waves that are like this, top to bottom, plunging waves. Our brain does a whole bunch of calculus in terms of distance from that impact point. Now, I will always say that you will not beat the ocean. You are not going to go faster than you think. So always err on the side of, I'm not going to beat the ocean. I might as well hang back and wait until these 4 bounces happen, because the energy, the acceleration vertically dissipates after that fourth bounce with a wave this size. So it's almost better to sometimes turn around and go backwards, give yourself space between where the impact is happening and where you are. Duck dive the softer, easier whitewater, and then time your paddle out through that impact zone. That's a strategy, and that saves you a ton of energy. The other strategy is, hey, if I'm in that 3-second kind of window, all right, can I find that little bounce? Right after impact to the second one are probably your best bets. But on smaller waves, the second one is not very big at all. It's quite small. So your best bet is that first impact. Where you don't want to be is you don't want to be right at the impact, because it will take you down underwater. It'll pile you downwards. That's what this is. And then it pops up. Okay. So that is the Z-axis. So those of you that are experienced, you're like, oh, okay, I get it. But here's the science behind it. Here's the proof. Here's the evidence. This is awesome. Okay, so that was the Z-axis. Let's look at the X-axis, because that's the other one that I found extremely interesting. Just to remind you what the X-axis here is, as opposed to my level 2, the X-axis here is in the direction of wave propagation, meaning the wave pushes forward toward the beach or backwards towards the ocean. Okay, so we're following from the -1 second before impact, and there's 0 acceleration in any direction on the x-axis. Then all of a sudden, it rises up quite a bit. So what that means is that it's rising up positively, meaning that the IMU gets pulled up the face, and now it's at the top at, say, -1 seconds. It hasn't moved forward yet. In fact, it's gone backwards slightly right before that. It does go a little bit negative right before that -1 point. So think of it, if you're looking at it from the side, it's like the particle moves backwards a little bit before it moves up, and then it moves forward, right? And then when it's at the top of the wave about to overturn, it moves forward really fast, okay? That's what this increase in acceleration is, up until about the half a second before impact. About a half a second before impact, you can see it peaks out at about 4 Gs, 4 units, Earth acceleration. It says no units. I'm just going to say 4 units of acceleration. And then the acceleration drops dramatically down, all right? And it drops dramatically down right before the point of impact. Because what happens is as it's pitching over, the IMU shoots toward the beach, and then it goes down, right? And so it goes down, and the X axis stops. It doesn't really go forward toward the beach anymore. It goes down, and so it's kind of, that's what this drop is. It drops down to zero again, and then it hits impact, and look what happens at impact. Holy cow! Does that go backwards by negative 14 units? I mean, that is an enormous magnitude. It basically, right after impact, it's zero is impact, and it kind of goes backwards. It kind of goes from just before to just to impact. It kind of goes backwards a little bit, but then it goes backwards really fast. At I don't know what that is, 0.3 seconds. I mean, it's like barely anything. And then it's still going backwards, but the acceleration is slowing, and then it crosses the zero axis, and then it goes forward. And then it goes forward really fast at about a half second after impact. And then that acceleration drops, and then it goes backwards again just before a second. And then it goes forwards again just after a second, and then it kind of fiddles around. It goes backwards for a little bit, but the accelerations are really low. Still going backwards at 2 seconds. Goes backwards at 2 seconds. Then it goes forwards again at about 2.5 seconds. And then it has that kind of drop again, that drop in acceleration really fast, where it goes backwards pretty quickly right before 3 seconds. And then it kind of goes up and then stabilizes. So if we think about how that is in comparison to the vertical, so at -1, it goes up and it goes backwards. Then it goes up and forwards. And when I say forwards, I mean toward the beach. And then it drops down, hits the impact, and it goes backwards but up really quick. So it kind of does this kind of circular thing. It kind of goes, this is showing that it's the first orbital motion. It goes backwards and up, and then it goes down and forward, and then backwards and up, and then down and forward, and then backwards and up, and then down and forward. It's exactly the bounces, but it does the bounces in an orbital motion almost without too much chaos. So right between 1 and 2 seconds, there's a bit of chaos where it's kind of just not really going toward the beach or away from the beach. It's just kind of staying where it's at. And then all of a sudden it goes towards the beach, and then all of a sudden it gets pulled back. So it's like if you felt when you duck dive or turtle roll and you're in the whitewater and it's like pulling you towards the beach and then away from the beach, right? Or, out to sea, and then it's pulling you back and forth and up and down. That's this. So I always have thought about waves like orbits, like circles, right? And, when it breaks, it's obviously in that orbital or elliptical kind of movement. The energy is, everything's in there. And so when you're duck diving, you're actually trying to go down and under and then use that energy to come out the back. What this is showing is that even in the whitewater, you can use the whitewater to help you dive further under. Let it push you down, and shortly thereafter, it's going to push you further out to sea. It's going to push you negative. So when the blue line goes negative, that's when it's actually pushing you through the back of the wave. When it goes positive, it's pulling you back towards the beach. So think about this. If you did a duck dive and you came up out of the duck dive while it's pulling you backwards and it's pushing you down, that's the wrong timing. If you do the duck dive as it's pulling you up and backwards, that's the right timing. Or it's pushing, or you could say when it's pushing you down, which is here, and out the back, which is here, right before that 1 second mark. So if you miss the bounce, you can use the second roll to help you get deeper in the water by using its energy. Now, again, if you come up between seconds 1 and 3, you're going to get rolled backwards, you're going to get rolled down, you're going to get rolled up. That's not the time to release your duck dive from being underwater. It's going to be after 3 seconds. And I tell this to all my clients when I teach duck dive, stay down longer than you think you need to. Because there are second and third rolls that happen. And if you come up during one of those rolls, right what we're seeing here on screen, this is the evidence right here, you're going to get pulled back towards land. That's the positive, right? You're going to get pulled back towards land, which is positive in this graph. While at the same time, it's going to send you down, right? And that's not what we want. We want, when we're duck diving, we want to go out to sea, right? We want the blue to be negative. And we may use the verticality to get us down deeper, right? But we want this acceleration going out the back, not pulling us back towards land. So in summary, there's this rolling motion that happens 3 or 4 times within 3 seconds. And it's all about the timing of that. If you stay down underwater, let's say you miss the impact zone and you miss the first bounce. The second bounce is going to push you down pretty far. Let it push you down. Then stay down there, and you have to have a good technique where you can hold that low plank with control of the board. But you need to stay down for another 2 seconds before you release and come up when things are a little bit more settled. That's what this is showing for that type of wave. Now, for a spilling kind of wave, I don't know what it looks like, but I'm looking forward to what they come up with of what a spilling wave looks like. This is a plunging wave, very, overturning wave. Spilling wave, it's going to act differently. The whitewater is going to act differently. But how cool is this? And then the y-axis, the red line. The red line we're going to look, and this is positive is further out to the shoulder and negative is further into the pocket. And you can see that the red doesn't really do too much. It goes out to the shoulder, and then it goes back to the pocket, and then it goes out to the shoulder. And then there's a bit of acceleration at about the 1 second mark and at the almost before the 3 second mark. And those are where it's pulling you back into the pocket really quickly. So if I'm paddling out and I'm duck diving, it's actually keeping me relatively in the same location, left, right, except for at the 1 second mark and at the 3 second mark. That's what this is saying. So it pushes you to the right a little bit. It pushes you to the left a little bit. But it left is being positive, right is being negative. But you're going to get pulled back into the pocket at seconds 1 and 3. So it's going to pull you to the right. So this is helpful if you're at a reef pass. I remember this one spot in the Mentawais that I surfed. What was the name of it? But it was weird because the whitewater actually didn't pull you out to the channel. It pulled you into the impact zone. So, depending on the currents and stuff, it could be that y-axis is pulling you more in the negative acceleration back here in the negative direction, meaning toward the pocket more. And this is actually evidence showing that, it's pulling you back into that power zone at the 1 and the 3 second mark. And so I wouldn't worry so much about that, but just having the knowledge that, hey, I'm getting pulled back into the impact zone is quite helpful, I think. Now at Ocean Beach here in San Francisco, I think it pulls you back into the impact zone on top of the longshore currents and the tidal currents. And so this is evidence of no currents around longshore or tidal, and it's showing that it's pulling you into the pocket at seconds 1 and 3. So if that's the case, and then you compound that with longshore and tidal currents, that's going to be an issue. That's definitely an issue. So this is kind of the main thing with duck diving, turtle roll, strategy even. If I'm on a longboard, I'm not using duck dive. I'm not even using turtle roll if I don't have to. I despise the turtle roll. I have a few other techniques that I try to do back here. So beyond 3 seconds, I will literally turn around and head towards shore to remove myself from this whole situation and within this 3 seconds. But you can also see here that at least at Surf Ranch, after 3 seconds, it lets you go. That's not the case in the ocean all the time. Sometimes there are some spots that will roll even more than this. But the point is that if this is a small scale model, let's say this is a model, this is a test, that it'll eventually let you go after a few rolls. The number of rolls and the magnitude of those rolls is going to be dependent on the bathymetry, the height, the direction, many other ideas. But this is kind of like the model that we would follow. Here is one more illustration of that, and it kind of shows the x-axis of a molecule. And you can see here at these are the different moments of impact. So the top one is the movement of the x-axis when looking at it from the side. So x-axis is toward the beach, away from the beach. So this is kind of, it almost looks like a wave, and then when it bounces, right? The second one here, x notch, this is the derivative. This is the acceleration of those points. And so it kind of gives you a sense. The distance between these points is shows how quickly it's the velocity in between those moments in time. So it gives you that sense of velocity. But just looking at the top one, that kind of shows you what a wave looks like. Like you can see it kind of goes backwards first, and then it goes forward and up, and then it really spits out forward, and then it hits and it goes backwards, like we said, and then it bounces, but not as high. You know, that's the first bounce. It doesn't go as high as the wave itself, even though sometimes you see white water that is that high. The actual water particle, at least the IMUs, didn't go that high. And if you think about if you're heavier, you wouldn't go that high either. And then it bounces again, and then after moment 8, it goes away. So really, I think interesting as another one. And that's kind of like, okay, that's essentially it. The steepening and overturning of surface gravity waves. And they were looking at, sediment transfer, turbulence of the, how is the turbulence moving the sediment for both shallow and deep water. And they wanted to know, are using these IMUs, these wave drifters, is this accurate? So this is fantastic. They did it. I think that they outlined a few limitations and things that they could do next time, but we're not going to get into that. What we're going to get into is the next study. So this one was done, I guess it wasn't, it was accepted in January 2023. The Scripps Institute of Oceanography. This one is called Cross-Shore Wind-Induced Changes to Field Scale, Overturning Wave Shape. Blah, 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 blah. It feels like when you hear adults talk in Charlie Brown, it's like wah 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 wah. So in layman's terms, this is offshore versus onshore debate. And we all know what the results of offshore and onshore are, but there's some really, really cool stuff that comes out of this. Now, again, I think Surfer Magazine did a thing, the Inertia did a thing. This study confirms what we've always known. Offshore waves are better. But this, we're going to go into a little bit more of the details. So in this second one, it gives you a bit of terminologies here. Capital H is wave height. Little h is water depth. We talk a lot about in level 2 the relationship of wave height versus water depth. It's approximately 1.28 is the ratio of a wave breaking in a certain water depth. So h is equal to about 1.28 big capital H, or wave height. 1.28 times the height of the wave is what the water depth is. So it's about 3/4 of the water depth. So we talk a little bit about that, but that varies based off bathymetry and such. But they're using that as a benchmark here. They did it for 22 waves. There were a few waves where the basin hadn't settled, and so the wave broke, not in the right place for them to analyze. There's an overturn area A, which I think is kind of cool, and then an aspect ratio, which we've talked about on the podcast, called vortex ratio. So that's the width of the vortex versus the length of the vortex. That's the aspect ratio. The overturn area A is basically the area that's the pocket. How big is the pocket? So I'm just trying to kind of like make it a little bit easier, because there's a lot of words in here. And let's see here. So the first thing I kind of came down to, this is a whole bunch of background still. And again, here they're looking at, once again, they're looking at how offshore winds and onshore winds might move sediment, how the turbulence moves, and how it moves sand as well. So how it kind of shifts sand around. Do onshore winds shift sand differently than offshore winds? Does it move sediment differently? So does it change sandbars, in other words? What does the turbulence do? How strong is the turbulence, right? Based off of these two things. And I think, anecdotally, we all know, okay, yeah, offshore winds probably mean that the turbulence is stronger. The injection is stronger. It's moving sandbars because it's hitting and it's breaking sand. It's moving sediment because it's blowing off the top, and it blows out to sea a lot further off the top, right? And that's anecdotally. We can kind of come to those conclusions. But once again, here they're using science. So what they did is they set up this vertical, what they're calling a rig. So they set up this vertical, like, tower, I guess you could say. This tower, let me see if I can find a picture of it. Yeah, there it is. So I'm showing a picture of a left, and you can see there's this kind of thing in the water, and they set it up. It's like a vertical pole, and it goes up above the wave. And on the right, you can see it here. It comes up through the mid face of the wave. Well, that's actually in front of the wave. And it comes straight up, and it goes above the wave by a certain amount. And so they just kind of placed this thing. Is there another picture? I thought there was another picture of this. I can't find it. So we'll go back to the beginning here. So there's this pole that they're doing, and they're doing it on the left and they're doing it on the right. And they did it on different days. On one of the days, it was a little bit more offshore. I mean, the predominant wind there is going north to south, so it's offshore on the rights. But they did get a few mornings where it was a south wind, so it was going from the south end to the north end for the left to go offshore. So they did get a little bit of onshore on the right and a little bit of onshore, or more onshore on the left, a little bit of offshore on the left, and a lot of offshore on the right. So they kind of related these 22 waves across the 2 different days. They related wind speed. They're calling it a crosswind, and they wanted to determine whether it changed the overturn area, the aspect ratio, whether it accelerated at certain points of breaking, and so they went through. Let's see here, kind of as an aside, I thought that this picture here in Figure 1 is showing, here is the rig right here with the black dot. So I'm showing an overhead view, like a drone footage looking down of the left. And it shows the black dot, I don't know, like, what is it showing? 10 meters away from the wave face. But here below that in D, in Figure 1D, it shows the bathymetry from right to left. So on the right side of the photo is the plow. On the left side of the photo is the quote-unquote land, right? The rig is at 0. And it shows the bathymetry at that point of where the rig is, which is kind of neat. So it shows, if you look to the left, the bathymetry goes down. So after the rig, it goes deep. And so it's deep just to the left of this, and then it gets shallow, 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 and then it goes dry, over to the left. To the right, it's shallow right where it is, but then it drops off dramatically as you approach the fence. So, if you ever go here, this is really specific to Surf Ranch, but this is showing just a little bit of insight into the bathymetry. So if you're surfing this wave and you're at this point in the basin, if you go way out onto the shoulder, that wave's going to die out. You're going to lose energy. See how the bathymetry drops. So that's just kind of a side, is like you want to stay tight to the pocket. So right here where it's shallow, it's about 1 meter deep. It's probably a barrel section of the wave. My guess is it's about 3 feet of water at this point. Might be the barrel section, might be right before the barrel section. It's just this one point in time. But as an aside, I thought that was kind of cool. The other cool thing that I saw, I'm going to scroll, where is it? Yep, here it is. Figure 2. A and B. So now we're looking at the left wave on the A figure and the right wave on the B figure. And you're looking at a straight on view of the left and a straight on view of the right. You can see the rig in each one. The rig is shown right here. And then in a kind of a pink diamond, it shows the point of impact of the overturning wave. And just take a look at the distance difference between onshore left wave and an offshore right wave of the distance. So the rig doesn't move. It's basically in the dead center between the left and the right. And so the left and the right are supposed to break the same. But just because of the right wave being offshore, the point of impact is much further to the right when we're looking at the wave, meaning it's further into the pocket's way back, right? And away from the shoulder. So if we're using that y-axis that we did in the last study, it's really negative. It's way over towards the pocket where the whitewater is. On the left, where it's onshore, it's pretty darn close to the rig. It's really close to it. Maybe a meter and a half from it looks like. Whereas on the right, it's like 2.5 meters from the rig. So what I see from that really is just that distance of what they call the splash up, the first splash up. The right, you can ride so much further back in the pocket when there's offshore wind. Right? And we always say, oh, why? Because it holds it up. Well, here's some evidence. Here's some scientific evidence showing you of that happening, right? And we haven't exactly determined why, but there's some hypotheses that are coming out of this study, which is cool. So that I thought was pretty cool. The other thing that I really found interesting was the height of the rig was different. So on the left here in this figure 2, they did say further down in the study that this was done on different days, these two pictures. And the height on the left ended up being taller than the right, which a lot of people think, oh, offshore winds make waves stand up taller, but not necessarily. In this case, they actually determined it probably had more to do with the wave settings. They used the same wave profile in all of these studies, but that there might have been a plow setting that was slightly off that made this left a little bit taller, just slightly taller. It's about 2.2 meters versus 2 meters on the right, which I found interesting, that people say, oh, it's the same wave every time. It's like, no, it does have slight variances. Like it really does. Offshore, onshore, different parameters on the wedge that they're on the plow that they use, how much disturbance the water has before the wave runs plays a big role in the wave. It's not It's not an easy wave to ride. But what we can get from this is that if it is onshore, you got to be out here more on the shoulder. When it's offshore, you can tuck back in and feel safe that you can be further back in the pocket and be in the right place. And so you can translate that directly to Surf Ranch, but you can directly translate that to any ocean environment as well. It's going to be a similar behavior of wave. Of course, in the ocean, there might be slightly different bathymetry, so don't be like, oh, he told me to stay back in the pocket. Well, not if there's a big feature underwater that's going to like rear up and go shallow on you. You gotta hit the gas and go, right? But what this is saying is that you have more time in the pocket. You actually want to ride further back in the pocket. Now, the figure 2, figure 2 kind of shows you the area. Now we're getting into kind of the area of the pocket, and this is a UAV image, and so it shows kind of like it's like a heat map of the wind. On the left, it's onshore, and you can kind of see like the orange is faster wind speed, the blue is slower wind speed, and then you have kind of in between. But you can just see kind of the area of the face here is a lot smaller between the first kind of area here. It's a lot smaller area of face on the left when it's onshore. Then look at how wide this is on the right. The face is so much wider. The area is so much wider and larger when it is offshore. Again, these are things that we've anecdotally and visually seen, but this is showing proof behind it. So the left is breaking down the line, and it's less steep than the offshore wind. The offshore wind has much more steepness at a certain point. Now we get into kind of the next part, which is showing that steepness. This is just further evidence of what we just talked about, meaning that the pocket's bigger on when it's offshore. This figure here, figure 4, is now looking at the left and the right waves now from the side. So as if we're looking into the barrel from the shoulder, almost straight on, we're looking straight into it. It's showing the movement of water particles in terms of speed of the overturning wave. So the darker the color you see here, the closer it is to you. The closer it is to, let's say, the photographer or the person. This diamond is signifying where the midpoint of the wave is, the mid face of the wave is. Now, both, I believe that, yes, both of these, let me make sure I get this right. No, we're not there yet. So the right is still offshore and the left is still onshore. So there's still a barrel on the left. You can see the barrel. But the water particles, when it creates the barrel, are further away from the viewer than the water particles on the left. The face of the wave is further towards the beach on the left than it is on the right. On the right, the face of the wave, the face of the wave is closer to the beach. It's steeper. So the mid face of the wave is steeper on the offshore wave than it is on the onshore wave. And that's where that diamond is showing. So the diamond is the x-axis, so it's the wave propagation towards the beach, away from the beach. So towards the beach is to the right of the view, and away from the beach is to the left. And you can see the mid face of the wave is much further out to sea, whereas here it's the mid face is more, and you can see even the steepness of the wave is taller. Same thing here in the previous time. So it's a steeper wave. That's what this is showing. So I thought that was kind of cool. We're getting down to now the time. This is now the right. So this is figure 5, and this is the time. This is showing A, B, C, D, E, F at different moments of time. And so as the wave progresses up, it's not quite standing up yet. And then about a second later, it's standing up. About a second later from that, it's starting to now hook over. And now it's starting in frame D, it's starting to throw over, and then throw over some more, and then throw over some more. And you can see how kind of light the particles get. That means it's getting further away from us. So what this is saying is that the offshore winds on the right, or offshore winds in general, are going to pull the wave back into the pocket as the wave forms more, which means as it gets more and more hollow, you want to actually hang back further in the pocket. Rather than when it's on shore, you want to kind of shoot for the shoulder more. Again, these are anecdotally, these are things that we have learned. Finally, we get to figure 6. Now, figure 6 looks pretty similar to the vortex ratio. It describes the width of that barrel versus the length of that barrel. We're going to scroll down to figure 7. Yeah. Figure 7 is showing offshore lefts and offshore rights. And it's showing that cross-section of width versus length. So all this is showing is that these were four different shots of offshore winds, just showing that, the top 2 are offshore left, offshore right, and the bottom 2 are onshore left, onshore right. And you can see in the onshore, there's still a barrel there. But when they show you the details and the results of the width to length ratios, in the offshore waves, they actually visibly evidence that there is a larger area, 1.74 square meters on the left and 1.74 square meters on the right. And the width to length ratio is 0.51, meaning it's a wide barrel. On the right, it's 0.49, so pretty close to the left. So the left is a little bit wider than the right in this instance. On the onshore, the area is only 1.46 square meters versus 1.74 square meters with the offshore. I mean, that's a pretty significant difference in terms of just spacing inside the barrel, right? So if you're a big person, you don't have as much. And this area is the area of the pocket, I should say. So it's not. I take that back. It's not. Doesn't have anything to do with the size of the person. It has to do with the size of the steepness. So think of the y-axis distance and the z-axis, and that's kind of what that A is, the area of the pocket. So it's steeper and it's wider power zone when it's offshore. When it's onshore, it's smaller. It's a smaller area. And that's what we just talked about, how you can go further back in the pocket when it's offshore because you have more power area. Now, the width to length ratio of the vortex is significantly less, almost half when it's onshore versus offshore. 0.51 and 0.49 for offshore, 0.35, 0.36 when it's onshore. So not quite half, but pretty darn crazily close. And the moment of the barrel, they're just saying, is about it's about 2 degree difference of the 40 degree benchmark. So they're just saying that at this moment of the wave, it's apples to apples or pretty close to it. So, I thought that was kind of cool. What else did I find that was really neat? So figure 8 is showing the depth versus wave height, and kind of the variability of waves. I mean, it's showing cross shore lefts and rights here, how the lefts are they're breaking a little bit taller, but it shows you kind of this variability of height. This is what I thought was kind of cool. Within the same general depth, the heights of the waves can differ. And it just kind of just further proves that these wave pools are not the same all the time. They're different, and it really depends on your day of and the way that the water's moving. So I thought that was kind of cool. Figure 9. No, I'll skip figure 9. Figure 10. Figure 10 is now showing the offshore rights holding, like they were held up longer. Their area to height squared, the rights held up a lot longer, a lot higher, a lot wider area than the lefts that were onshore. So that's really what that's showing. And then the width to length ratio was better on the rights than on the left. So that's all that's showing there based on the wind speed. So, some really, really interesting things. A couple things that they kind of pointed out as limitations was the fact that this is a soliton wave versus a progressive wave. And this is where they're talking about the water depth before the wave breaks. So in a progressive wave that you see in the ocean, the water level right before it breaks might drop down before it then pulls back and up and over, right? So it kind of pulls water off of the reef, or it pulls water off of the sandbar, and it kind of goes out to sea a little bit, whereas a soliton wave doesn't do that. It basically pushes in the same direction of the wave propagation towards the beach almost exclusively. And so when you combine this observation and this, what they're saying is somewhat of a limitation because it's not quite representative of an ocean wave. And you combine that with the previous study where it actually proved that it does go backwards a little bit before it goes up and then throws over. It just kind of further indicates just a little bit of knowledge of how waves move, how particles move, which I think is pretty cool. And then finally, the last thing, this is figure 11. And this one, man, I went nuts on this one. What this is showing is before the wave turns over. So at its kind of peak height with an offshore wind, it's showing pressure bars. And it's showing basically the closer the pressure bars are together, the faster the wind speed. And you can see from a heat map, the darker the blue, the lower the pressure. So if you've listened to this podcast and you listen to the one on pressure, what did we learn? We learned that high pressure loves to fill in where low pressure is. So if we're looking here from the side, at about 4 meters in front of the wave, you can see that the offshore winds are pretty evenly spaced about. The pressures are pretty low at this point, and the wind speed's pretty steady. As we get to 2 meters in front of the wave, you can see the curve of the wave starting to kind of slowly come up, and you can actually see the wind speed slow down here a little bit at the base of the wave. Interesting. The wind speed is starting to slow a little bit. The pressure stays about the same as it did about when it was 4 meters out. Now we go back to, I would say about 3/4 of a meter, maybe just before a meter in front of the waves. You can see that the wind speed starts to increase and the pressure starts to drop. That's what we would expect, right? So if the pressure drops right at the peak at, say, 0, see how dark blue that is? It's negative 600 pressure. See how close these bars are together? That wind speed is whipping. So in other words, what this is saying is at the very peak of the wave, the wind speed's moving the fastest. But what this is saying that actually means a little bit more is that the pressure changes. You get very, very low pressure at the very tippity top of the wave. So if there's a reduction in pressure right at the crest of the wave, the air is accelerating. the streamlines converge, so faster and faster air. That's what this is showing. Now, this suggests that the surface pressure can impact the wave shape overturning. So this potentially also explains the higher overturn areas and aspect ratios for offshore winds. It has to do with pressure. And that it comes back, I'm totally nerding out here because I don't know how many podcasts ago I talked about how pressure is everything when it comes to surfing. It's all about pressure. This is showing that pressure makes a big difference. Now, they didn't do the same heat map for an onshore wave, but I would guess that the pressures wouldn't be as different. It would be back from the back of the wave. The pressures would be reduced. I think the pressures would be reduced. The wind acceleration would be lower at the crest. And it would affect the wave in a different way. Right? So in summary, this, again, the surface pressure that we see here right at the crest, right where it's kind of holding up, right? That's that holding up of the wave. It's right before it's about to throw over. It's the surface pressure that potentially explains this. Unbelievable. I love it. And then they finally, they talk about on page 24, somewhere around here in the summary, they talk about how offshore winds, they're going to be changing the beach. Their sediment suspension, they're going to be moving waves around the skewness and asymmetry of the sandbar. They're making, when it's onshore, it's smaller, less energetic overturns, leading to reduced water column turbulence and less sediment suspension. That's basically saying onshore winds don't move the water around as much. There's not as much column disturbance. Column meaning verticality of the sediment in the water column, meaning the verticality of the sediments vertically in the water. In contrast, offshore winds lead to different shoaling skewness and asymmetry, as well as narrower surf zones, larger, I forgot what that was. Energy dissipation, DW, larger average energy dissipation, energetic overturns with strong turbulence injection, and increased sediment suspension. So these offshore winds, they blow more things around, and they make the wave break, makes it break harder, so that it then moves the beach around, and it moves the sediment that goes along with it. So they did what they did. They came with this conclusion, and that's pretty cool. Like I said, I went into much more detail on kind of the basics of this. The basics were offshore winds are good and onshore winds are no good. But hopefully you guys were able to learn a little bit about wave knowledge. And wave knowledge is going to help you a lot more with decision-making, strategy, which technique to use, when to use the techniques, how to surf the wave differently. Should give you confidence to hang back in the pocket a little bit longer and give you confidence to get out on the shoulder if it's onshore a little bit more, and to try to get ahead of the wave. So hopefully it helped out. I had a lot of fun doing this. Hope I didn't bore you to death. And if you have any questions, send me an email, shoot me a call. I'm open to discuss surf and surfing paddling specifically. If you guys are interested in paddling technique, check out the website at surfingpaddling.com. And until next time, I'll see you in the water.